Okay, fine. So we have another 3 minutes, so I'm set. Okay.
Yes, yes, please.
Yeah, so Priya will also be giving, I'll start off, then she will do, and then
So
between us,
another. Sort of together, but should be fine.
hello, yeah.
Hi, Prof. I think it's about time. Whenever you're ready, Prof.
Okay. So let's start. Hello, everyone. I think there's still 1 more minute to go. Livo, we'll wait for a minute and start. Okay.
Not a problem, Prof.
You can see the presentation.
Yes, I can.
Okay. So it's machine learning and deep learning. This presentation you can see, right? Yeah. Okay. So hello, everyone. I'm Najam Hassan, and today we'll be discussing deep learning. In our previous sessions, we spoke about machine learning, and I'll have two presentations for you. One, a very short one on uh, what is machine learning and what is deep learning, the comparison between the two to get a second position. So basically, deep learning is a special type of machine learning. Yeah, so machine learning is the bigger set and deep learning is a subset of it. All deep learning is machine learning, but not all machine learning is deep learning. So what's the difference? In machine learning, we train machines to learn patterns from examples using selected features or measurements. In deep learning, we train machines to learn patterns using neural networks with many layers, often directly from raw data. So machine learning, it has structured data. For example, you may have for stars, you have star ID 1, 2, 3, 4, and magnitudes of those 20.13, 19.87, 21.34, and so on. Then we have color 0.45, 0.21, and so on. We have redshift, and we have signal to noise ratio, and so on and so forth. So these are the measurements and catalog properties. So as you will see that machine learning usually works very well with catalogs, with tables, where you have featured data. So we have these featured engineering. We have magnitudes, color, redshift, concentrations, so on. And the machine learning models train on features. They build these decision trees. They have algorithms like random forest and SVM, and then it does classification and regression and various things based on features. While in deep learning applies to data, essentially raw data. So you may have inputs like images, we have stellar spectra, we have light curves. We don't have features. There's no manual feature engineering here. And the neural networks, look, you feed the raw galaxy images or stellar spectra or light curves, and the neural networks sifts through this and understands the features. It tries to build models on the basis of it. So we don't provide the features to it. It learns from raw data and automatically discovers the usual features and representations. So, like I said, machine learning works well with structured features, high performance with information, hard-crafted features, and often needs feature engineering, requires domain knowledge and careful feature design. Interpretable and efficient models are often simpler and easier to interpret. Coming to deep learning, it learns from raw data, automatically discovers useful features and representations. It uses deep neural networks. There can be multiple layers. It models complex nonlinear relationships, and it excels with large complex data sets. It's especially powerful for images, spectra, time series analysis, and so on. So both approaches are complementary. The best choice depends on the data and the problem we are studying and the amount of available data which we have. So deep learning is very efficient, very good when we are dealing with large amounts of data. So for example, when I'm giving you, if I give a regular example, suppose we have oranges, apples, tomatoes. We specify in machine learning, we specify that an orange is, the color is orange, the texture is rough, and it is round. For a tomato, we say the surface is smooth, the color is red. So we specify the features. While in deep learning, without specifying the features, we give all these fruits, and the neural networks understands that there are certain objects which have a coarse surface, color is orange, and they are round, so it categorizes it, understands that it's an orange, and one which are red and distinguishes between apples which are red or green or from the texture and so on. So in deep learning, it understands from, we don't have to specify the features in it. So the basic difference, in machine learning, the teaching is teaching a computer to learn patterns from data without explicitly programming every rule. An example rule, we avoid hard coding, and we specify if a star is red and faint in class, to classify it as M. We don't specify that. Instead, in machine learning, we say, instead of writing every rule manually, we provide examples of stars with known classes and let the models learn the pattern. In deep learning, a neural network-based form of machine learning with many layers, it learns complex patterns from raw data, useful for images, spectra, light curves, and simulations, and often reduces the need for manual feature design. You don't have to specify the design. The networks themselves understand it and do it, right? So natural example of apple and orange, which I gave. In the machine learning, we specify the color, size, shape, texture, and you say if it is red, if it is orange or green, what it is, if the size is small, medium, or large, and we specify the features. Then train a model such a decision tree, random forest SPM or logistic regression is done, and you have classifications and so on. Okay. In deep learning, we just give the raw image itself without giving the features that it is red, orange, or green. The early layers learn the edges, right? We could say that if it is a round edge, then you should consider it to be an orange, and if it is slightly oblate, then to tomato. And then the middle layers learn the curves and the texture and so on, and later layers learn the whole fruit shapes and the finer details of that. So the key difference is machine learning often depends on human design features, and learning learns features automatically from raw data. So for example, we have star 1 and 2, and we have magnitude 14.2, 10.8, and so on. We have the color 1.5, 2.1, where we give the features of parallax, proper motion, and then we specify that if you have all these features, then to take it as a main sequence, and otherwise treat it as a giant and so on, right? So in machine learning, you specify you have these features which you use to train the models, and then once it is trained, it is used to you run it on data which is yet to be understood, and the systems breaks them into different categories, groups, and so on. So machine learning view, the model learns from numerical columns such as magnitudes, color, parallax, and power motion, while and a typical input is a structured table or measured astrophysical quantity. So machine learning methods in astronomy, we have seen random forest, we have seen DB-scan, HDB-scan, Gaussian mixture models in our previous lectures, K-means, clustering, and so on. And we also have these SVMs. And this random forest is generally used in star, galaxy, or quasar classification to give objects, these tables where it identifies it as a star or a galaxy or a quasar. These SVMs I use often for separating stellar populations, separating them into different bins, different types of stellar populations. K-mean clustering is used for grouping stars into clusters, and SDB scan, DB scan, finding open clusters or moving groups, or finding members, differentiating members of a star cluster from the field stars, and so on. Or in a population, in a region where there is a lot of, we can identify and find more clusters, substructures in it, and so on. So DB scan and HDB scan. And I think in previous sessions, you have seen these examples of these. And similarly, we have these Gaussian mixture models for modeling stellar populations. So the important point is traditional machine learning can be very powerful when the input features are informative, clean, and physically meaningful. Coming to galaxy morphology, we all know that galaxies come in many shapes, sizes, colors, reflecting their formation histories and the physical processes that shape them. We have spiral galaxies, which has a disk, which have a disk-like structure. It would have a bulge at the center and a halo. And it has these prominent, beautiful spiral arms and active star-forming regions. While elliptical galaxies have circular or elliptical features, they have smooth light profiles. The distribution of light is pretty even as you go from center to out, it falls in a very beautiful way. They are dominated by generally old stars, and we don't find much gas and dust, or we don't see them concentrated as we find in spirals in specific regions. Irregular galaxies, they are asymmetric shape, They are clumpy star-forming regions. They are rich in gas and dust and so on, and they don't seem to have any specific spiral arms or, right? They don't seem to have a smooth distribution like these. So we have the traditional machine learning for galaxy images. We have the concentration index, how the light is falling from center outwards. What is the electricity? What is the Sersic index? The color and asymmetry. And using these features, we train models on these features. And then the trained systems identifies and bins galaxies from a host of images into spirals, lenticulars, irregulars, and so on. In deep learning, we don't have these features. We don't have numbers to indicate concentration index or Sersic index or electricity and so on. We feed directly galaxy images into the neural networks, and the networks, they themselves may learn that there are spiral arm edges and bars. They have smooth elliptical profiles. They have tidal features and merger signatures, or they have clumpy star-forming regions and so on. So from images itself, it finds out that there are certain images which have clumpy regions, as some have smooth profiles and so on. And the system itself understands from images without having to give the features numbers as a Sersic index or electricity or so on, and can find out that there are certain types which are spirals, certain lenticulars, ellipticals, and so on, right? So it learns on its own directly from images. So galaxy morphology contains complex structures, and raw images carry information that may be hard to summarize. So deep learning works very well when we come to this kind of we have very large surveys these days of like SDSS and so on. We have many galaxies which images, and earlier there were human experts who would look at it and decide that it's a spiral or a lenticular or an elliptical. It was time consuming and very tedious. And now the surveys are becoming very extensive and large, and it's becoming impossible to use human experts to do that. So the machine learning, deep learning algorithms are being used to do this very efficiently and so on. And since uh, the galaxy morphology has a lot of complex structure, and these raw images carry this information, these machines are very good at identifying and grouping them into different features. For example, it could be a spiral, but spiral also has spiral with bars, spiral bars with a ring feature in it, and so on and so forth. So the deep learning algorithms do that. Similarly, we have these stellar spectra and we have spectral classes, right? We have, depending on the temperature of the star, more than 30,000 Kelvin to 3,500 Kelvin. We have O, B, A, F, and so on. And we have these stellar spectra, and the deep learning algorithms, they can see these spectra, the absorption lines and emission lines, and can categorize these star spectra into different bins and very efficiently. So spectrum records intensity of flux as a flux function of wavelength, and spectral lines carry information about temperature, composition, and the activity, the motion of the star, and various things. So in machine learning, we have these features like H alpha, equivalence weight, calcium triplet strength, line depth, continuum slopes, and so on. And these features are used to train systems in machine learning. And they are used to predict the stellar type, temperature, metallicity, and so on. While in deep learning approach, we do not specify these features. We feed the whole spectrum into a neural network, and the neural network learns a set of subtle line combinations, the absorption lines, where is it appearing, at what location, and so on, and captures the broad continuum shapes and can exploit the weak patterns difficulty, which is difficult to define manually. Similarly, deep learning can be very well used, both, in fact, machine learning, deep learning, both can be used when we are uh, uh, looking at variable stars and binning them into different types. So in one, you have the periodicity variables and you have the features specified which are used for machine learning. For example, what is the periodicity, what is the amplitude, what is the skewness, the transit time, and so on. And we give these features, and the machine learning uses these features to uh, bin the different spectra into different groups. While in deep learning, you give the transit curve itself, and by the profile of it, the machine learns the various features in it and predicts whether it's a variable star, what kind of a variable star it is, whether it's an exoplanet candidate or what class does it belong to. So, yeah, like I had already specified, in machine learning, we have these features, period, amplitude, rise time and decline time, skewness, Fourier coefficients, and then used to classify Cepheids, RR Lyrae stars, eclipsing Barydes, or exoplanets. While in deep learning, we feed the full light curve directly into the neural networks, and it learns from the dip shapes, and it learns from the periodicity and noise patterns. It learns the transit signatures by itself, and it's very useful even to detect anomalies or to classify them as the light curve is that of a variable star or a eclipsing binary or so on. So if you compare the main differences between machine learning and deep learning, the aspect relationship, machine learning it's a broad field, and deep learning is a subfield of machine learning. Input data in machine learning is often structured features. Yeah, it has structured features in it, while in deep learning we have raw data. Uh, Future designs, usually the features which we have are human design ones, and in deep learning they are learned automatically by the machine. Uh, Machine learning generally works with relatively smaller data sets compared to that of deep learning. And deep learning usually needs large data sets, right? Because in machine learning, we are specifying the features, and we are specifying specifically if it has these features, then you have to classify a certain object as whatever it could be, a quasar or a star or so on. While here it requires a large data sets for it to be able to sift through it and identify the differences, nuances, and different profiles. So machine learning can be run on normal computers, while deep learning requires very powerful GPUs. Often more machine learning is often more interpretable, and deep learning it's harder to interpret. In machine learning, we use catalogs, analysis, clustering, classifications, and so on. And in deep learning, we deal with images, spectra, simulations, light curves, and so on. So a simple aid to memory is machine learning learns from features, while deep learning learns the features itself. Um, so a simple analogy in machine learning is like giving a student a list of measurements and asking them to learn a rule. If the color, size, parallax, period, line set is something, then it is a certain object. While in deep learning, it's like showing students many images of spectra, light curves, and letting them discover useful patterns themselves from galaxy pixels, from full pixels, and the raw light curves, and right. So they have to understand the features themselves without specifying, right? So that's the basic difference. An important distinction: machine deep learning is not automatically better. Machine learning is not old, and deep learning is not always the best choice. It depends on what kind of data we are handling, what kind of problem we are studying, and they are complementary to each other. So machine learning can be we can use it for Gaia catalogs, data with all these features, parallax, proper motion, color, and so on. And we have random forest, HDB scan, Gaussian mixer models, and all they may work very well. While in deep learning, we handle raw images, say from Hubble or JWST or Sloan Digital Sky Survey or LSST. And deep learning can be useful because the spatial patterns are rich and complex. So machine learning, yeah, so the final summary, which is a repetition of that. One, you train machine learning models from engineered features, while deep learning, using multiple layers of neural networks, discovers those features by itself. Okay, so this is for the difference between machine learning and deep learning. I'm sure you must have got a clear idea about it. If there are any questions, I'll just see. Uh, okay, I don't see any questions. So, okay, let me proceed then with now we come to deep learning, because machine learning we have done in our previous sessions. So a small presentation on understanding what these CNNs are, convolution neural networks, and how we use it in astronomy. Yeah. So reiterating this point, why do astronomers require deep learning techniques or machine learning? Basically, the idea is the same. We have modern telescopes and surveys which are creating enormous amount of data, and we are getting enormous amount of image data sets, and we are required to classify millions of galaxies from a field, uh, identify faint gravitational lenses in that, see whether gravitational lens is there or not, or it's an artifact, detecting supernovae and variable stars, and searching for exoplanet transit signals and so on. So we have tremendous amount of data, and these machine learning techniques are very useful in sifting through this data and understanding them. So a simple definition for CNN, a convolutional neural network, is a neural network designed to learn patterns in images. So instead of reading an image as one long list of numbers, a CNN looks at the nearby pixels together and tries to pick up the features. A convolutional neural network learns useful image features step by step, right? So you have the image, and the convolution filters sees different features in it. For example, you may do a Gaussian blur to it, and the sharp features may get hidden, and we can get an overall a smooth feature of the object. Then you can run another filter through it, and which enhances the edges or contours in that. and we could have yet another filter. So using different filters, we see different, you see the object at different levels of resolution. And from that, it builds up feature maps. And then you have these dense layers of these feature lamps, which joins together to give you the complete picture. And from these layers, it uses these dense layers to predict what an unknown image, if it's given, it predicts whether what category. For example, a neural network may be trained to understand morphology of galaxies, and it understands the difference between spirals and lenticulars and ellipticals. And we are going to see examples of that. And then we use these neural networks for predicting from the unknown uh, images. We have images, we feed it to them, and it classifies them as a spiral or a lenticular and so on. So one thing it's important to realize is that images, the CCD images, these astronomical images which we have, are essentially array of numbers. So, for example, the image on the right side of this beautiful uh, galaxy um, uh, is it is basically a two-dimensional array of numbers. At each pixel, it records the photons it collects, and actually this uh, I'll show you how to get these numbers. These are exactly these numbers. If you use IMSHO method, you can reconstruct this image, right? So this image and these are exactly the two things. And each number stores the brightness. The bright stars have larger values, and the empty sky has smaller values. And then there's noise behind which gets added to it. So you may not have any pixel which is actually giving you a zero because there's some background noise and so on. But by doing some image processing, you can remove the noise or background and so on. Okay. Similarly, this image which we have here of a ring, a gravitational lens ring, which we are getting Einstein ring, is nothing but a array of numbers, right? So each location, there is a number given there. It's a data type of float 32 type, and each pixel has a certain amount of photons which is collected, and that is the number which you see here, right? So these are two equivalent things. So in the key idea in convolution is we convert these images, these input images are essentially, like we said, are numbers, and we convolve it by a kernel, and then you can get the convolved features in it. For example, we'll run an example and I'll show how it is done. So this is the 3x3 convolution kernel, which I run it on this image, the input image, and what we get here, right? And here we are seeing the features of it, and we can very clearly see the ring here. So early CNN layers may learn um, simple patterns such as where are the edges, where are the blobs, the gradients, the bright spots. And the later layers combine these into objects such as spiral arms and galaxy cores and arcs and stellar trails, right? So early layers looks at edges, it looks at corners, it looks at bright spots, it looks at small textures. And the later layers will look at the spiral arms, the galaxy bulge, whether it has a bar in it or not, and various things, and nebula filaments and so on. Okay, so, and then you run these CNNs on a set of images, and it matches those features. It convolves it by the same thing. And if the features are similar, it can classify it as spirals or spirals with bars or so on and so forth, right? So now for a moment, I will stop and go to stop this presentation and use a Python notebook, which I'll share with you. And okay, so um, yeah, so we'll see then how these are used for how different filters are used to extract feature extraction. So here's a Jupyter notebook, and we are importing the important uh, things. Import NumPy as NP, and from PIL import images, and Matplotlib we use that. And I've downloaded an image of gravitational lens, and I've kept it exactly from where I'm running this Jupyter notebook from. That's why the image path it's right there. But suppose you are having your data sitting somewhere else in /mnt data, yeah, so you'll have to give the whole path here, right? So in this case, I needn't give the path because it's specifically sitting where we are. And then we load this image. So yeah, we use image.open and specify where that image is sitting, and we convert to the RGB, and we are converting that into the array. Okay, so and if you print this image array, you will see that you have an array of numbers, right? So basically, this image which we have is basically all these numbers, right? Or if you say plot, or even if suppose I had I had said IMG, uh, you will see that you are getting that image here. Okay, yeah, this is the image, and yeah, or you can use the plot imshow command to see this image. Okay. In the next block, I convert the RGB image to grayscale, and I'm converting to this zeros, zero, zero, yeah, 1 and 2, and these are the three, and I'm converting into the grayscale, and you'll see we have got the same thing in grayscale. Okay. And yeah, so you notice here it is. And now we'll use this convolution kernel. The kernel is also a NP array, right? The whole thing is now converted to an NumPy array, and I'm using this kernel -1, -1, 1, 1, -1, 8, 1, 9, right? And I'm using this kernel, I'm defining this kernel, and I use this, yeah, I'm defining convolve 2D image by this kernel. And after you convolve it, you see this is what we get, right? So we have the input image, and we have this convolution kernel which we have, and what we get are the convolved feature maps. Okay, so this is the one, and here we can see these features. So by using different kernels, yeah, so these kernels are filters. By using filters, you extract different features in that. So in my other Jupyter notebook, I'll show you how we can make different kernels and how can we get different features for images, right? So we'll do the same thing, say for the spiral galaxy. So basically it's the same kind of file, but the galaxy which I'm using spiral galaxy here. Yeah, so image spiral galaxy.jpg, and I'm loading it in this and converting it to grayscale. And here you can have a look at the image IMG, right? You see, this is the image which we have. And now I'm using uh, a Gaussian, I want to apply Gaussian blur to it, right? So, so this will reduce the tiny star noises before the edge extraction, right? So all the tiny stars which are there in this image, right? The small bright objects, it is going to blur it out and it will, right? And then we have another Somble kernel, and this is to detect the directional edges. In which direction are the edges curved? Okay. And then we have this Laplacian kernel, which highlights sharp structures in it, right? So if you apply any one of them, you can apply, say, only one Laplacian to that image as a exercise, you can do that. So for the image which we have here, you can apply one kernel at a time and see how the image changes, right? So I'm doing that in one step here. I'm applying in step one, I'm using the Gaussian kernel. And then in the second one, I'm Sobel's feature extraction, where we are, right? And then we have the Laplacian features. And then we are normalizing the whole thing and seeing it. So when we run that, here it is. So this was the original image. This is in the grayscale. And this is after run by passing it through the Gaussian kernel, right? It's smoothing out the whole thing. You can see the whole thing is looking blurred. So all these sharp images are gone. So, okay. And then we have this Sombels, which pulls out the edges, right? You can see how the spiral arms are curving and so on. Then you have the Laplacian one. And this is the combined feature map. So by using the combined ones, now this can be used to run it on different galaxies. And if it sticks to this pattern, then we can say it's a spiral-like galaxy of a certain feature, right? So if you want to pull out done spirals with a bar or spirals with the rings, you have to use different kernels to extract those features, right? So in the same one, I'll just comment the spiral galaxy, and now I'll open elliptical galaxy, yeah, which I have downloaded from the net, and I load it in image, and I plot that and see if this is an elliptical galaxy. And I'm using the same three kernel apply the convolutions to this, and we display the results. And here you are, you have the original image, you have the grayscale image. This is with the Gaussian one. This is with the Sobel's edge features, right? This is with the Laplacian edges, and this is the combined one, right? So this is what, yeah. So the take-home point here is every image which we have in astronomical image which we get from CCDs it's an array of numbers, and the filters which you can pass through are also arrays of numbers, right? We are using NumPy arrays to create this, and we use that to convolve it with that. And right, so this is the one which shows how you combine these displays and right and see it. Okay. Now coming back to our presentation. Yeah, so that was just this thing to show you. And yeah, so important thing which we also have to keep in mind is when we are running these neural networks, to construct these confusion matrices. So when you run them on the images, you construct these confusion matrices. And yeah, so what does this say, right? If you see on the x-axis, you have the predicted ones, and on the y-axis, you have the true ones, right? So these are the irregulars, ellipticals, and spirals, and these are what we are predicting. So what you see along the diagonal, the object is spiral, and we are predicting a spiral. There are 86 of those. Pretty good. Okay, so here if you add up 86 plus 7 plus 4, you will get all the total number of spirals which we have. Yes, 7 plus 11, 11. So 97 of them are there, from which 86 it has correctly identified. In ellipticals, we are predicting these to be ellipticals, and 88 are correct. But 9 of them we are predicting them to be ellipticals, but they are actually spirals, right? And 8 of them we are predicting it to be elliptical. I mean the neural networks is predicting 8 of them to be ellipticals, but they are irregulars. This is where it's going wrong. So off-diagonal elements are where the neural networks is going wrong, and diagonal shows where it is going right, right? And similarly so on. So if you add up 86, 88, and 88, you will see that we have 262, 262 of these. And out of 300 galaxies, the 262s have been correctly identified, right? And that gives us approximately 87.3%. So our neural networks, this confusion matrix shows that this neural network is working pretty well. 87.3% of the time, it is predicting the right thing is the right thing. In less than 13%, it is going wrong. Further, this confusion matrix tells us that the maximum error, the major mistakes it is making, is between ellipticals and spirals. That's where it is going wrong. So here we are saying it is elliptical, but it is 9 of them as spirals. Similarly, when we are saying these are spirals, 7 of them, these are actually elliptical. So if you see the numbers, we can see that the biggest mistake it is making, the problem it is having, is between spirals and ellipticals. So you can train those models, improve the kernels better to train them, so that this error can get reduced even further. But overall, 87.3% is a pretty good estimate. So a gravitational lens can look like an arc or a ring around a massive galaxy, and we have many telescopic images, and the probability that the image contains a lens or not is what we are trying to see. And the neural networks gives us, identifies and tries to say whether it's Einsteinian ring or not. Right? This is useful because lenses are rare and in large surveys contains millions of images. So it goes through these large number of images which we manually cannot sift through, or it will be very tedious to do so, while the machine just goes through and picks up these features and classifies them. Similarly, it can do that with light curves. When a planet crosses in front of a star, the star becomes slightly dimmer. So the dimming of a star, is it because of a planet transiting it, or whether it's because of the spots on the star, or whether it's it's a variable star itself. So from the light curve, the pattern of the light curve and the depth and intensity, you can make out what it is. And we have many, many observations and deep neural network with the deep learning techniques, and the CNNs are very efficiently uh, used to classify them as what kind of a transit they are and whether it's exoplanet or a variable star or so. So the training of a CNN, as we have already seen, you have these labeled images. We run through the CNNs. It predicts, and then you compare it with the true labels. And if it is predicting well, then you are fine with the CNN. And if there are errors, if it's making some, then you make changes to the CNN, train them with more objects, and then you see whether go on till the time you achieve the kind of precision in prediction you achieve, you are satisfied with. So the model changes its filters again and again until its prediction improves, right? So here it is. So this is Keras style example where you have convolved 2D, right? And yeah, max pooling and flattening dense. We'll use this in one of our Jupyter notebooks. And this exact Keras style kernels we'll use to identify three classes: spirals, ellipticals, and irregulars. Okay, so just a few things which beginners often make mistakes. So be careful of that. When you are training, if you have very few images you are training your CNN with, right? If there are too few, then your CNN will not be intelligent good enough to do it, right? So you should have sufficient number of images for training, right? You have to feed in a lot of images so that it can pick up the features properly, right? Because there can be very subtle nuances which are to be recognized and found. For example, a spiral galaxy may have a ring in it or not, may have a bar in it or not, or elliptical galaxies may have dust lanes in that, still it could be an elliptical. So you need to feed it with a lot of images to do that. Similarly with the spectra and so on. Testing of on images that are too similar to the training sets. So if your training sets and the sets on which you are testing it, whether your neural networks are working fine, if they are too similar, then you will get a false feeling that your CNN is working well. So your uh, testing images also should have some kind of variability nuances in it. For example, suppose you have just trained on spiral galaxies which are face on, and you are testing also with spiral galaxies with face on where spiral arms are really very obvious and so on, then you are not really seeing whether your CNN is fine enough or not. You also have to test it with these spiral galaxies which are slightly inclined where you know, it needn't be a face on 90 degrees, but it could be at 60, 30 and other angles too, for testing and checking how efficient and how good your predictions with these CNNs are. So in ignoring class imbalances, for example, many normal galaxies, but few lenses, then forgetting that CNNs can learn telescopic artifacts instead of astronomy. So you should keep in mind that if there are artifacts which come in these telescope images, CNNs may take it as a certain feature. So you have to be careful with that. Okay, so if there are artifacts and reporting accuracy only without checking false positive and false negatives, that again is a blunder. We should be careful about it. You have to report the false negatives and false positives too. So good practices in astronomy and using CNNs is split data into training, validation, and test sets, right? So usually training you'd use 70 to 80% for training and 20 to 30% you use it for 20, 25. Generally 75 or 80 is a good one to train, and use the remaining 20, 25% for as training sets for validation. Use real noise and telescopic conditions. Yeah, realistic noise you should use to remove the noise in it, right? Don't create artificial ones, homogeneous noise, but use something which is very realistic. So when you are removing noise from it or using filters for noise, use the realistic noise ones. Inspect the misclassified examples, right? So if your CNN classifies a certain object, say a stellar spectra as RR Lyrae one, but it is not for some. So you inspect that a bit carefully and see why is it going wrong, so that you could correct your networks, and compare with simpler baseline methods. Use explainability tools to see what image regions influence the prediction. So the key messages, the CNN is powerful, but astronomers must still check whether the model learned really astrophysics or not. They should not pick up artifacts and do it, right? So don't use it as a black box, but use it discreetly. So, like I said, just a recap of what we have said. The take-home message is CNNs are designed for image pattern recognition. Convolution filters learn local visual features. Deeper layers combine simple features into complex astronomical structures, like we saw in the case of elliptical galaxy, the spiral, where we ran with different features, and then we combine those simple features into the complex astronomical structures. And CNNs are useful for identifying the morphology of galaxies, finding gravitational lenses, finding transients, right? Supernovae and other objects, of finding exoplanets uh, for stellar spectra and so on. So good validation is essential, right? So keep in mind that you have to, yeah. So with this, I will stop here, and and then I'll go on to, if you want to go now. Oh, yeah, I'll do one more, and then you can do. Yeah. So I will run another Jupyter notebook where we will run in a more sophisticated way. Um, yeah. So galaxy morphology classification. So there is a good paper called Convolution Neural Networks for Galaxy Morphology Classification. And on that paper, I have built this a simple uh, Jupyter notebook, which we'll share it with you. And I have this in two versions. In one where we are using TensorFlows and PyTorch in it to run these CNNs. And in this particular one, I'm doing it without the TensorFlows and PyTorch, because this requires a little more of computations. And um, when you are running it on your machines right now without preparing, you may have trouble. So this particular notebook will run on any system, uh, and you don't need internet for doing so. And we'll be essentially using NumPy and Matplotlib. And the model here is intentionally small, and it's basically educational. It trains a real simple CNN layer from scratch using NumPy so that you can see the core ideas without fighting deep learning installation issues and so on. The other one, I will share it with you, which is there on Google Colab, which is running well on Google Colab. In fact, it's running on my system too. But if you start running, you may have issues. So I'll leave it for you to tweak around and play with it later. So let us run through this. The paper which I have mentioned on top, it says that there are about 37 different features which are essential for these CNNs for doing galaxy classification. But in this one, I will basically use only 4 features to make it simple and so that the whole thing runs well, right? So, yeah, so we are using import math, which we had seen in our first session, importing NumPy, matplotlib, plyplot for plotting. And we have from NumPy this libstride tricks for sliding window view and so on, right? Seed, we are fixing at 42 so that repeatability when you run this thing again and again with the random seed fix, which is 42, you get the same results. But when you want to rerun with a different seed, you can do that, but for repeatability, right? These two commands are basically just to see the version and yeah, it's nothing important here. So like I said in the article which I will be sharing, there are 37 output attributes which are used, but in this, to keep this notebook uh, um, beginner friendly, we use only 4 simplified morphology outputs, which are the smoothness, disk, looking at it edge on, and the spiral features in it. Yeah, so only on basis of these 4. So as a homework, you can try it for all 37 different ones. Okay. So the real Galaxy Zoo images are large and must be downloaded separately. To make this notebook run anywhere, we have created a small synthetic Galaxy-like image. And this is the 4 ones. And this block of code below is creating these 4 kind of ones. Okay. Okay. And this is what it does. So that it's creating 160 images, right, with 4 features in it, and the distribution. Yeah, the smoothness factor and this, yeah, the percentage in which they are there are given here, right? So it's created here, and you can plot these things, and you see these are the images which we have synthetically created, right? This can be done. You needn't create these ones. You can download actual images and train on that. But for simplicity and for running it fast, we have created, right? This looks like a spiral. This looks like an elliptical, right? Spiral with bar feature in it. Yeah, this is an edge-on spiral. And these are clumpy, irregular things and various features in it, right? These are the odd, right? This is the irregular galaxy. This is an edge-on galaxy which we are doing, right? So these are very simplistic images. Okay, this is an elliptical one, and so on. Okay, so then we train on 80% and keep 20% for validation. I'm doing that because that article which I have mentioned on top, it's they recommend that. They have said to train on 80 and use 20 for, rather than doing it for 90 and 10, right? So they right? Split behavior, it's better with 80-20 rather than 90-10. So that's what we do it in this. And when we run this, you get these mm, train ones, and we are building the CNN, a tiny CNN from scratch with NumPy. So this model is deliberately small. The image is trainable in 5x5 convolution filters, right? You have ReLU activation, you have 2x2 average cooling, you have flattens, dense sigmoidal output layers, right? So you have these four features in it: smooth, disk, edge on, and spirals. Yeah. So finally, it will break them into these four different categories. Um, and why do we use sigmoid? Because each output should be probability like value between 0 and 1. And we do not use softmax because these outputs are not one mutually exclusive class. Okay. So we have the sigmoid Z, and the prediction say we are getting the outputs here, and the first untrained prediction is right. These are the predictions out of that. And when you train on these things and run them, uh, it's running right at book 120. So you get the root mean square errors on the train sets and the validation. You are seeing the root mean standard errors, right? So you are seeing that validation is giving pretty reasonable, uh, the small errors, 0.43. Yeah, is right. See, it's becoming, initially it was 0.43, it has improved to 0.40, 3.7, it has come down to 0.23, right? So it has reduced to, it went through a series of iterations and it trained the CNN. So initially the errors were large in the predictions, about 43%. Then the second iteration got it down to 40%, then to 34 and so on to about 23%, right? So you may run it more for a longer time to improve this even more. Okay. And then this will give you the plot history and show how as the time is progressing, how the mean standard error is decreasing. And right, so you are seeing how it is falling from error, which is from the trained models to the validation ones, right? And how the root mean square curves are decreasing, right? So it's improving tremendously. Yeah, so it's coming down to almost 23%. And this will, okay. And here you see that smooth, identifying whether a galaxy is an elliptical galaxy, whether it has a smooth feature or not, it is 0.2 for 24%. Disk is also about 24%. Edge on, it is efficient at 30%. And spirals, it is doing a good job as 0.04. I mean, right? So about 4% of it, right? So these are the root mean square errors. And you can see the uh, graphically, right? So we are running it on, and this is prediction, and we can visualize the convolution filters. These are the convolution filters which we uh, moved it through. Okay. This is the pictorial representation of this convolution filters which we used to find out, right? And very, very easily we can see now that this is a elliptical, this is an elliptical, this is a spiral, this is an edge-on, and this is again, this is an edge-on, right? Edge-on, and this is some kind of a irregular, right? It has edge-on, but there are some other features here which shows some, this must be an irregular galaxy. So With this, you can, yeah, so these are the filters, and this is the visual map of these filters. And you can use this, and you have a block of code here, which you can uncomment and run it. But for that, you'll have to download images from the Galaxy Zoo, from HDSS and so on, and specify the data directory. You'll have to uncomment this, see where you are keeping it, and give the path to that. Or if you are running it exactly from your where your Jupyter notebook is, you needn't define the path. You can directly put it in a semicolon into it, and you can run this with this. Okay. So with this, I will stop for now. So final takeaway, CNNs are useful for galaxy morphology because they learn visual patterns directly from pixels in the real galaxy zoo task. And those patterns are used to predict many human world population attributes, making the task closer to multi-output regression than ordinary image classifications. Right, so I'll stop now. And are there any? There's a question in CNN-based galaxy scanning. What are the advantages and disadvantages of converting RGB to grayscale? Actually, you can run it even on the RGB, but essentially, the reason why I'm doing it is the images which we have, the CCD images which we get are basically black and white, they're in grayscale, right? And the images which we see in pretty pictures, these are the images which you, because any CCD image is only a measure of photons which are coming in. So you take it through different filters and you construct these colored images artificially, right? We are using these RGB combines to do that. So the enhancing these features to make these images beautiful and all, that's why we had the colored ones. So I was reducing it back um, uh, to the grayscale because that's what basically those images are, right? So it is better to deal with the grayscale because the RGB ones are the ones which we have synthetically created, while the actual images are in the grayscale, right? So yeah, that is the basic reason why we are converting it to grayscale, and then we are running these networks, right? Because all these kernels also which we are running, they are basically in the grayscales. Okay, those kernels are not going through the RGB filters, right? So it's better to get it to grayscale and go. Yeah. Okay, so now Priya ma'am will.
Hello. Hello, everyone. Okay. Yeah. So we'll continue from where Sir left, and we'll be now talking about some other thing, which is what is called principal component analysis. Okay. So I am just a minute. I'll just share my screen. And what happened? That you didn't give me. No, no, now it's too late. It's okay. So, what are we going to talking about is principal component analysis. Okay, this is a very useful thing because a lot of you all for your capstone project, you could do something of this kind. And we'll first of all talk about what exactly is principal component analysis. I hope you can, yeah, you can see my screen. And then we'll actually see about what are we doing. Okay, so so let me briefly describe what's principal component analysis. This is something if those of you all who are math students, if you consider in terms of linear algebra, right? This is like your basis vectors. It's, for example, in three-dimensional space, if I were to draw a lot of points, right? But I finally understand that these 3 points, I mean, every point can be just represented by 3 terms, right? Which is your x, y, and z. So your basis vectors are x, y, and z. Those are the principal components for any point, right? Your x, y, z axis, right? So exactly in that way, what you basically do is if you have multi-dimensional data, okay? By multi-dimensional data, I mean, for example, data, say you have data about stars or galaxies or whatever it is, and let's say you have 50 columns of that data, right? And in today's time, that often is the case because we have a lot of data, right? We've been talking all through this course how we have so much of data in various data sets, right? And therefore, it can happen that you have, for example, 50 columns of data about galaxies, right? The point is you want to figure out which of these columns are important, right? And that means basically looking for principal component analysis, which is what we also call dimensionality reduction. It's, for example, if I have 50 columns, right? I realize that my data, the 50 columns are not important, right? I figure out that supposing some 5 columns are important, which could be a combination of these 50 columns, right? It's not that I select 5 out of the 50. The 5 which I select could be a combination of these 50. But I finally figure out that that is the basis vectors in which I need to describe my data, okay? So what happens if in your data set you have a lot of features, right? For example, look at this. You have multiple colors over here on the left, and on the right what you see is these are your dominant colors. So you figure out what your dominant colors are, and now you can see the left hand image all can be represented by a combination of the right hand image, right? All the colors in the left panel can be described as a combination of the right panel, right? So that tells you that the right panel is your basis vector, right? And once you have your basis vectors, every point on your thing can be represented as a combination of these basis vectors. That's the basic point. So for example, how does this principal component analysis work? What does it do? It removes redundancy, it improves computational efficiency, because now instead of working with 50 columns, for example, now you work with only 5 columns, like I said earlier, right? So if you've got to deal with only 5 columns, it becomes obviously easier for you to handle the data and try to make some sense of it. Like we've been saying that from the very beginning, our entire purpose is that we want the data to speak, right? We want to get key information from the data. So when we reduce the columns of the data, right, we are basically improving the computational efficiency and our capability of looking for patterns in the data. Fine. So like I said, it uses linear algebra to basically transform data into new features, and these new features are called principal components. Like I told you, the principal components can be a combination of the data, right? So it finds these components by basically doing what is called looking for eigenvectors and eigenvalues, right? Students of y'all who are from maths background, you'd understand what that means. But that basically means that if you reduce your matrix to your eigenvectors and eigenvalues, you can, you can break down the covariance matrix. So we'll anyway talk about it in a little bit of detail. So what happens, let's say we have, and what we also do is when you do this, since your columns can be all of different kinds, right? They could be different dimensions, they could be with different values, right? Some may be less than 1, some may be within a billion, some may be, they could be all kinds of ranges. That's why what we do is, before we do principal component analysis, we first standardize our data. What do we mean by standardize our data? We make our data, set it in such a way that the mean of the data is a 0 and the standard deviation is 1. How do we do that? Is we actually look for the mu, or the mean of the independent features which we have, and using that we define our z, which is x minus mu divided by sigma, where sigma is the standard deviation of the individual features. Once we standardize our data, so the first step is to standardize the data. Once you standardize it, you actually calculate what is called the covariance matrix. What do we mean by the covariance matrix? I spoke about that last time also. If you remember, we had with our data, we did what are called pair plots. That means supposing if you have 5 columns, you make plots of 1 versus 2, 1 versus 3, 1 versus 4, 1 versus 5, 2 versus 1. You make combinations of each column with respect to another. Why you're doing this? To basically see whether a column can be represented as a function of another column, right? For example, supposing your first column is a set of values and second column is just the double of it, right? Then you immediately, with a covariance matrix, you can figure out that your second column is redundant because it's just first column multiplied by 2. So covariance matrix basically gives you an indicator whether any column is basically a function of the other one, right? And in that way you can check out which of your columns are unique, right? Okay. So we'll be doing this with our data set, but this is just to let you know. So we calculate our covariance matrix, that is with respect to all the features. We check out what are their dependencies, right? So it could be positive or it could be negative, it could be 0. Okay. Now after this, what we do is we find out what are called the principal component, right? So the principal components could be 1, 2, 3, whatever. And it is described in the terms of this, which is your eigenvalue equation, which is Ax is equal to lambda x, where lambda is basically the eigenvector, right? Some of you all may know it. In case you don't know it, don't worry too much about it. It just makes it simpler, easier to understand if you understand this thing. So basically you find out the eigenvector, eigenvalues for your matrix. Once you do that, you pick up the top directions and we transform the data, okay? We transform the data, that means we do A into X and we actually find out the top K components that capture all the data variants, okay? And we convert it like this. So supposing if we had a data set which had 2 columns, one was area and one was radians, we actually define a principal component PC1 and a PC2 and represented by these black axes. These are the axes, these are these things, and here are our data points. So then I describe things in terms of this. So if you see in terms of this, PC1, which is a single component, it can describe all these points. I do not need PC2, right? So PC1 captures the maximum variance in the data, meaning it holds most information, while PC2 captures the remaining variance and is perpendicular to PC1. Yeah, obviously these principal components are perpendicular to one another because they are like basis vectors, right? So the spread of data is much along PC1 than along PC2. That's why PC1 is chosen for dimensionality reduction. And by projecting the data points, we effectively transform the 2D data into 1D data. So now we have to only handle one-dimensional data. Instead of having two-dimensional data, we convert it to a single dimension. And then with that single dimension, it obviously becomes easier for us to make sense of our data and actually look for some patterns. Now, the good news is that in Python, you do not have to write the code for principal component analysis, for example, because it is all available in the libraries in Python. So what are the packages you'll need is NumPy, Pandas definitely, and you need scikit-learn. We've already spoken about it. In scikit-learn, there is a package called standard scaler, which is used for scaling our data. If you remember, I told you our data has to be scaled. Before we do anything, we have to scale our data because the range of different columns or different quantities could be different. Similarly, we also have to do the scikit-learn decomposition, which imports principal component analysis, is one of the modules in that. And then from there, we pick up model selection and we pick up all these things. So this is just a simple example. I'm not going to run this, but I'll just show it to you. Supposing here we make a data set, height, weight, age, gender, right? So we have all our parameters, height, weight, age, and gender, right? And the question is, if we want to, if I want to parameterize things about a person, for example, how many parameters do I need? If I know the age, can I predict the height and weight? Or, for example, the gender, right? So, what are the important values which I have to have? How many are there, number one, so that I can predict the rest, right? So, for example, if I know the height and weight, can I predict the age and the gender, right? Which is probably possible. Or, for example, if you know the age and the gender, you know a 25-year-old female, for example, can you predict what would be the height and the weight? Okay. See, we are not talking about outliers, okay? Outliers, we'll talk about it differently. So we are going to look at the regular trend, right? So if I tell you I have a 35-year-old man, you should be able to, can you tell me what is the height and weight? You can, right? And therefore you can see that here when I have 4 columns, in advance what you know is I basically need only 2 columns, right? For example, if I know age and gender, I can predict height and weight. Similarly, if I know height and weight, I can probably predict the age and gender, right? So anyway, we progress. So this is our data set. We have 10 data points for which we have height, weight, age and gender. First step, I told you we need to standardize it. What does standardization mean? Standardization means that the mean of all the data has got to be equal to 0 and the standard deviation has to be 1, right? So what do? I first of all drop gender because gender is not to be standardized. It's a category, right? So we don't standardize it. The remaining things we can standardize it, okay? So we can transform it. Now we apply the PCA algorithm, which is already available in Python, and we use that to actually find it. And you also find out what is called the confusion matrix, which will compare actual versus predicted labels. That means if I've used age and gender to predict height and weight, how well do I predict it compared to the real values, right? So I do that and I compare it. I get my confusion matrix. You can see that, for example, your predicted label female is 0, male is 1. So here I have my false positives, false negatives. You see, on the whole, it has done it perfectly, right? That means if you had a female, the true label was found, and here you have this. So this has done it pretty well, and we can visualize the PCA result. So for example, if you plotted height versus weight, right, or whatever your feature was. What did this thing hit? We plotted it, height versus weight. You can see a range for males and you can see a range for females. This is basic on the classes. The classes are the 2 categories, male and female. So you may put it like this, and this is before PCA and after PCA. So now the PCA actually gives you a combination of these. So advantage in this is, again, you have reduced the number of dimensions and therefore you have reduced the complexity of computations. So this was a simple example. We'll now go on to our astronomical example. Okay. Now in our astronomy example, we are going to use a particular data set, which is galaxy spectra from the SDSS. SDSS is the Sloan Digital Sky Survey. Okay. Now again, for your capstone projects, you could do an exercise like this, like principal component analysis for different data sets. And in AstroML data, right, this basically you can actually Google it and find it. You will see there are whole sets of data sets, okay. You can Google look for AstroML, which is astronomy machine learning. In this itself, you can have a look over here. There are various data sets. So for example, there's a data set for Sloan Digital Sky Survey, which is what we are going to use in this exercise, which is SDSS spectra. What they basically did is that they took spectra of galaxies, right? And they also do photometry across 5 filters. The filters are UGRIZ. Okay, these are the 5 filters. And they also did spectra. So your 5 filters came along these bands, and this is the spectra. So SDSS spectroscopic data is actually available as FITS files. You'll have already seen what are FITS files, and they're indexed by 3 numbers, the plate, the date, and the fiber number. So you can actually use this command in Python, which is called fetch SDSS spectrum. This is in the AstroML package. Okay, so you'll have to obviously load AstroML, and then you will use that to avail this data. So you can do fetch SDSS spectra, and you can actually use this to fetch a spectrum. For example, get a spectrum of this type. You can also avail SDSS photometry. Okay, photometry means what? See, spectroscopic data means flux versus wavelength. Okay, so this will be a FITS file, which is an image file. The other thing is what you can do is photometry. Photometry is what is it going to give you? It's going to give you the brightness in different filters. Okay, so that will mean magnitude in different filters. Like I told you, SDSS has 5 filters, UGRIZ. Okay, so it will give you the brightness in these 5 filters. So you could also get a data set by fetching the SDSS data, Galaxy colors. This one is SDSS spectra. This is SDSS Galaxy colors. So you can use this for getting data, right? You could also, so the spectroscopic sample, like you see, it doesn't, SDS is not an all sky survey. So it only covers part of the survey, and only part of the sky you can get, right? Not all sources will be available. So when you are accessing this kind of data, you should be careful. For example, if you're using Gaia, TUMAS, WISE, these are all sky surveys. But if you want to use SDSS, it will be only these fingerprints. Okay. So you could also have a look at the SDSS quasar catalog. There's a catalog of quasars, and you can say fetch DR7. This is the data release 7 quasar catalog. You can get this. You could do the imaging sample. So all you need to do is go to AstroML page, data sets, and you can look for these different data sets. Stripe 82, combined surveys. See, so all the different data sets. For example, if you want RR rays, this also, even in AstroML, you also have LIGO data. We are not covering any LIGO data in this session, but if you want to use LIGO data, you can also fetch LIGO data and actually use that in your analysis. This is for CMB, WMAP, temperature map. You can even get that data. So choose whatever data set you want from AstroML, right? And that can prove as a very good option for you to use for your capstone project. Okay? Have a look at the different data sets and see which data set matches with your interest, your liking. If you're interested in RR Ray stars, or you're interested in LIGO data, or whatever it is, have a look at the different data sets and you can use that to do your analysis. Okay. So I'm going back to my principal component thing. In this one, what we are doing is we are basically going to access SDSS Galaxy spectra. Okay. So what is this Galaxy spectra? Like I told you, it is flux versus wavelength. Okay. It's a plot of flux versus wavelength. What is the brightness you're getting in from the galaxy in different wavelengths? So what PC has to do is it has to compress its spectrum into smaller number of eigenspectra so that it identifies which are the important ones. Otherwise, the problem is the spectra has so much of information. If you remember, see, the plots look something like this. There's so much of information in it that it's very difficult for you to actually make some sense of it or look for some kind of patterns. So therefore, we want to look for eigenspectra. So first thing what we are going to do in this thing is we are going to download the SDSS spectra. We are going to construct mass spectral regions using the PCA-based reconstruction. We'll normalize each spectra. This is what we were talking about, the important one. Normalization, like I told you, means is the same thing like standardization. That means the mean has got to be equal to 0 and the standard deviation has got to be equal to sigma. Next, we fit it on a train split, evaluate explained variance and reconstruction, use that to interpret the principal components as eigenspectra, and then we project the galaxies in this low dimensional principal component space and relate the projection to physical spectral diagnostics. Find higher reconstruction error outliers. So now we will look for outliers also, and clusters galaxies in this physical component, principal component space, and compares cluster mean spectra. And use this to do a compact results summary or Markdown. Okay. So this is it's given to you in this notebook itself. The data we are using is this data set, spec4000.npz, but all the documentation is available over here. And here itself in AstroML, like I showed you, you can access different data sets, like I said, which you could use probably for your capstone project. More details about this one is described in this paper. I will not go into this detail, but you can have a look at it. It will help you make more sense. So these are the usual libraries which we are going to import. What are we going to take? NumPy, Pandas, Matplotlib, scikit-learn, the standard ones, right? So they are already installed, so there's no problem. So we are importing all of them. Like I showed you in the earlier notebook, we need to import scikit-learn decomposition, which has principal component analysis in it. Scikit-learn cluster, which has k-means. This has standard scalar also. And we can train test split. Okay, this is what we're going to do. So we'll do this. Now here what we are going to do is we will make a random number of columns. I put my seed to be 42. You can put it as whatever you want. And we'll display maximum columns 20 and dispersion of this thing. So that's what we are doing. And here we are downloading the data from the set. So all of you all have already got used to using Google Colab. Use this with Google Colab. So if you see here when I've downloaded the data set, I already have my data set sitting over here in this folder called data. And in the folder called data, if you look, I have my file. This is the file which has the spectral data, okay, which is spec4000.npz, right? So my data is sitting over here. You have to always remember that when you're using Google Colab data, all the stuff is just on the fly. So moment you log out of it, everything is lost. So once you run your notebook, whatever resultant file you have to download it, right? Otherwise it's lost. So you have to be careful about that. Okay. So here we are downloading and we downloaded our data. Now what will we do? We will compute the wavelengths in the data. Okay. It is there in the metadata file and we will write it 10 power this thing. Okay, so we will put it in this and we will reconstruct the spectrum. The spectrum has different parameters in it, the coefficients, the mask, etc. And you can this thing. So we can print the raw spectral shape, which is this. The reconstructed spectral shape, the wavelength range is basically from 3162 to 7936 angstroms, and some of it is masked. Okay, so we know it is about 15%. Now what we do is we inspect several spectra. So the spectra which we have, like I told you, it's flux versus wavelength. As part of AstroML, you know that some of these galaxies could be at higher redshifts, right? And therefore the wavelength of the galaxy then gets redshifted, right? And therefore what has been done in AstroML is for this analysis specifically, that we have actually transformed all the spectra to rest frame wavelength. That means we know what is the redshift of these galaxies and we have shifted the wavelengths, okay? Otherwise, if you didn't have the redshifts, then it would have been more complicated. Then you would have had to first find out the redshift of each individual galaxy and then shift each galaxy spectrum by the redshift amount, right? So it's basically lambda is equal to lambda into 1 plus z, where z is the redshift. So these ones have already been redshifted, so that will not give you a problem. Now we'll use this to actually plot the figure and you can have a look. Here are all the spectra, okay? So here you can see there's this thing of 5 spectra, which we've put over here. Now, if you remember, once again, let's just repeat what we were talking about. If you see that, like I told you earlier, if you look at these spectra, looking for patterns in this spectrum is very, very difficult, right? And therefore, what happens is when we are doing principal component analysis, we are reducing the number of columns or the number of parameters that we need to look for, right? But obviously with this, you can see some similarities in, for example, in this spectrum, and for example, this spectrum, the purple and the green. For example, this line, this is an absorption line which is present in this as well as in this. It's not present in this, right? So similarly here I have an absorption line, here I have an emission line, the red and the blue, this thing, but basically the purple is similar to the green. The red one is maybe similar-ish to this bluish one, and the orange one is maybe kind of similar to purple, green, and orange, right? So you can see that there are some similarities and some not similarities, right? So first of all, like I told you, the first step which we have to do is the scaling, right? Because you can see that all these spectral lines have a different height, right? So the amount of flux in a different spectral line is different. I want to scale it, and hence I'll scale it. If you remember, once again, the mean has to be 0 and the standard deviation has to be 1. So I'm scaling it, spectra versus wavelength. And if you see it over here, you have X-train and you are doing this. And you see the number of spectra, we had 4,000 spectra. And now the number of wavelength features are 1,000. So our trained spectra are 3,208. So what have we done? We have basically again reduced, this is an 80-20, in an 80-20 ratio, right? If you remember the last talk also, you spoke about training sets and validation sets, right? So my 4,000 spectra, I have divided it into two groups. One is 3,200, which is 80% of 4,000, right? And then 20% of it is 800. So what do? We use 3,200 to train, right? Then we run our thing and then we test that of the 800 test spectra, how many of them are correctly done. We already know the answer for these 800, right? So when we run the whole task on everything, we can check what is the answer I got for 800, how many of the 800 are retrieved. Supposing 750 are retrieved, right? Then I know that 750 out of 800, that means my level of confidence in my thing is 750 divided by 800, which is 94%. What happened? So you can see that I've done 750 by 80% because I know that for my validation set, approximately 750 out of 800 are being correctly done. That means my system is running 94% correct. You obviously cannot have 100% correct thing. Do not aim for that also. So by doing this 80-20 thing, we can even have an estimate of our error. That means I'm saying 94% I'm right, but I do have a 6% chance of being wrong, right? So depending on that, we are not doing this now, but you may do different, you may iteratively run the PCA again so that you try to improve your validation, right? But finally you'll converge at some value and you'll have that. That's okay. In science, in astronomy, even if having errors is not a problem, as long as you have an estimate of what is the error, right? So even if I know that 94% times I do it right, that's good enough. I don't have to do it 100% times. Fine. So now what am I going to do? I'm going to define physical spectral diagnostics, okay, for the interpretation. So what do? I have my 4,000 spectra. I'm taking the ratio of the average flux, red word of 4,000 angstroms, to average flux, blue word, right? So if you remember, this was our wavelength range. Our wavelength range was described a little ahead, 3162 to 7936, right? Approximately this. So now what are we doing? I'm breaking it into two groups, one which is less than 4,000 angstrom, this thing, and one is that. Okay. Yeah, okay. This scaling part, did I come out to this? Okay. So what are we going to do? So for each spectrum, we put a median value, which is, and then fit the PCA. So what do? Is we did this. Okay. So we did red word of 4,000, that means longer, or blue word, yani shorter than 4,000 angstroms. Typical values indicate older, redder stellar populations. We also check for, we know that the H alpha line is the 65-63 angstrom line, right? This is an important line because it's related to star formation rate in galaxies. So therefore, we would like to use the intensity of the H alpha line, which is an important indicator, okay? So like I said, it's associated to star formation as well as active galactic nuclei. So we know that that is an important indicator when I want to categorize the type of my galaxy, whether it's star forming or whether it's an AGN. So you may have some deliberate simple indices. That means through physics, if you already know which are the spectral lines which are important, you can identify them. Or you can put a broader site, like you put Redwood of 4000, whatever. You can choose as you wish. So here we define bands, which is X, the wavelength, low and high. So for example, this H alpha proxy is 6563. So here I am putting one at 3850 to 3950, this thing, 4000 to 4100. And now this one is Blueword and Redwood. And look at this one. This is the proxy which I'm putting for H alpha line. We know our H alpha line is at 6563 angstroms. And therefore this one I will put it here, 6400 to 6500. I can even make it broader. I can even make it 6600, 6700. Okay, I'm doing this plus this because actually it's a doublet. So I'm taking both the lines. So I'm taking this line and I'm taking this line. Okay. So I'm going to look at this H alpha excess. How do I do that? I do the H alpha line minus the continuum. I look at the continuum and subtract to see whether I have a height. So here my count is what? 4000 spectra. I have a mean value, standard deviations, etc. And I find out my this thing, the H alpha excess proxy and whatever. Okay. Now what do? I fit my PCA to the training spectra. So like if you remember, we said we are training it in an 80-20 ratio, right? So it's 3200 for training, 200 for this thing. So we retain up to 100 components. You have all those components. And it's usually enough to see the compression, this thing. So here I have my components. Like we've said, minimum is 100. We've already said we want at least 100 components, so minimum 100. And I take it based on the shape of X train, right? How many shape I have, and I do that. So I do that, find out my PCA transform X train, X test, and I run it. So this is for my training sample and my test. Test is the validation sample. So I use that and I find that out. So now when I see my PCA explained, you see this is the explained variance and this is the cumulative variance. Okay. So you can see that it comes off like this. Okay, we will explain that later. So now we want to find out what are the components needed. How many components do I have? You can see your cumulative value. This is the explained variance. Now what you can see is, look at this. You can see that when I have these things, this one has 71, 12, this is 7, 3, 1. And as you're going down over here, you can see this value has reduced. Basically telling me that these guys are not very important. These are the more important guys. These are not very important, the ones where this value is small. So I need to define the components needed. And I put a threshold, right? So you define a threshold. The threshold is the cutoff at which I want to reject components. So you can see that if I put my threshold as 1, then all these guys will go. If I put my threshold as 0.5, then these guys will go. So I have to decide what is the threshold I want to do so that I can understand how many components are this thing. Now this is something which you need to pay attention to, because keeping your threshold too high is also not too good, because then you will cut off a lot of things. And if you keep it too low also, you won't do a good job. So you need to look at it a little carefully. Even look at the plots. I'll show you the plots and use that to actually figure out what is the optimum threshold. So you can see here the threshold, we are plotting it for threshold 0.8, 0.9, 0.95, 0.99. So we've chosen 4 different thresholds to choose this thing. And we say for the thresholds, we are seeing what are the hits, we are seeing how does it come. Now we can see that if our threshold is 80, 90, 95, 99, here if you do 99, you'll need more than 100 components. While here the number of components, if I keep only 2 components, Then 80% will do 2 components, 90% 3, 95 4. So I need to identify or judge for myself as to how many components would I like to have for my data, right? It obviously depends upon the science case you're trying to study, what is the importance. It's not always that the correct answer is to have maximum components or minimum components. There's an ideal number and you need to figure that out. So that, but like I said, it depends upon the science case, what are you trying to see. Okay, so now one good indicator is to plot this. If we want to plot this, n components is not defined. Maybe I didn't run this. 1 minute, okay, here n components comes over here. So I'll run this and I'll run this. Then I'll be able to run this. So now what we are plotting, this is what is called a scree plot. A scree plot is like if you have a mountain and it comes down. What does it see this? What does it basically tell you? This is the explained variance. And this one is the principal component analysis, right? So this is telling you how many components should I keep for what value of variance. So for example, if I decide to keep 80 components, you see that my variance is not varying much between 80, 60, 40, 20. This is also what is called an elbow plot. So you can see it's not varied much. So definitely I don't need 80, 60, 40, 20. That is definitely not the right number of components I should keep. Ideally speaking, I should keep it coming up like this, where this will come up, right? I actually look for a number of components where there's a difference in the variance, right? Taking anything greater than this doesn't make a big difference because you can see the variance is about the same. So if this is like 15, anything greater than 15 is useless because the variance is about the same. So now how do I plot? I look for this elbow and I accordingly choose where will this thing. I can also do that cumulative plot. If you remember, we had these cumulative values here. And you can see the cumulative value again, it's similar plot. You can see what is the number at which you are getting the variance, right? So either you look at it from here or you look at it from here. These guys are almost reflections of each other, right? So this will tell you where is the value at which you will get a difference, right? So therefore, if you see in this, that you can see that if you see in the visualization, or you could even see in this list, 2 to 3 itself was good enough. Maximum you'd go to 4, but more than 4 actually doesn't serve any purpose, because more than 4, if you go up, you're getting it to more than 95, you are then, it doesn't serve much purpose. So this is probably 4 somewhere here. If this is 10, maybe this is 5, 4 somewhere here. This is about the point, right? It doesn't make sense to keep more. And so therefore, based on that, you see 2 or 3 principal components are good enough to see basic structure. If you want, that's the minimum which you need to keep. 5 to 20 you can keep if you want to, till 20. So that will cover this whole region, right? If you go it up to 20. And if you take more principal components, obviously, it could help you for narrow lines and unusual spectra. So now that you've done this, we are basically going to look for the eigenspectra, which is the eigenvalues we've spoken about earlier. Now here in the spectrum, we can mark some lines. Okay, these are important lines to mark. The calcium KNH line, H beta line, O3 line, these lines. So here you see in the plot, I've plotted the lines. Okay. So here you have your different spectral lines, 4000 angstroms. Yeah, these are your different spectral lines, right? So now when you're seeing your normalized spectrum, you can actually see the different spectral lines you have in it. And now when you see your PCA eigenspectra, this is the first 6. We also saw this earlier first 6. Now you can see now these PCA spectra are giving you exactly at these ones. You see that if this we've taken it as 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So you can see if I take these guys, then I can get it exactly at these values, which can cover these important values. Okay, so that will give me my eigenspectra. Now the other important thing is that each galaxy row now has a PCA score. A score is the coordinate of galaxy spectrum with the principal component, and you can actually do it to get your this thing. Well, I think I didn't run this. or I ran this. I ran it. Now let me run this one. What is the problem? D4000 is not defined. Where was D4000 defined? 1 minute, I'll just see. Maybe it was defined somewhere on top. Or let me just run all. Okay, I'll just run all and it'll come. Don't worry. So these are my PCA things. These are my PCA scores. So you can now see my PC1, PC2, PC3. Then I've put one for H alpha access, which I specially put in. And now you see when I plot it, you see the PCA score 1, PCA 2, and this is the proxy. Okay. So based on this, you have these different colors which are giving you your D4000 proxy. What is the D4000? Whether it's longer or shorter, right? Whether it's greater than 4000 or less than 4000. So that is also getting marked over here. Okay. And I can, here the proxy which we have put on it is PC1, PC2, but with the H alpha excess proxy. That means whether you're looking for, does it have an H alpha excess or it doesn't. So these guys have an excess, the green ones, while these ones do not have an excess. So I said if the excess ones are there, then that indicates that basically these are star-forming galaxies or they are AGN, right? And okay. So once you get this thing, you can interpret the thing. Like I said, 4000, it's capturing the continuous stellar population. Galaxies which large this thing are older redder populations. These are those. While H alpha captures emission line. The emission line is the H alpha line. And it separates star-forming AGN, right? And therefore, now we can look at the reconstruction quality. Like I told you, we want to reconstruct this thing and check the evaluation. So once we do the reconstruction, we can actually compare and see what is the variance and how well have we done our job. So we can actually see our 95 percentile test, and you can see that our values are pretty good. So I can see the PCA reconstruction, error on LDOT spectra, and here. So this is the median value, and this is what it is for the median. And this is for the best, for the 95th percentile, it is that good. Okay. We can also plot reconstructions for a few Handel spectra. So now what we've done is we have overlaid all these spectra, okay? These 6 spectra which we have overlaid them. We've put them one on each other. That is put together. And why are we basically doing this? Because we can look at all these positions, okay? So the held out spectra, you can do this. And you can look, these are all different spectral lines, right? And therefore, now the important thing which comes out of it is to look for outliers. You can see that, for example, you have this orange line coming here, which is not there for the other galaxies. Or you could have some line coming here, which is not there for the other galaxies. So I may use that to look for outliers, right? So we look for outliers, see how many outliers do we have, right? And accordingly, we can identify these different outliers, right? So for example, if you remember here itself, I showed you it was the orange galaxy, the orange one which had these outliers. And therefore, when we replot it, you can see it is plotted with the orange galaxy, right? So this orange one is an outlier, and we need to be concerned about the difference in spectrum, right? So your outlier could have maybe some extra unusual emission lines, or it could have some unusual stellar populations which are giving you those spectral lines. Or sometimes it could even be that there's some artifact, some, your outlier could be a faulty spectrum, a spectrum which has been taken in an automated fashion, but it has some artifacts or some calibration problems in it. That's why it's an outlier. And so therefore you can use this. You can also do, this is optional, you can also do unsupervised grouping. If I want to, for these 4000 galaxies, I want to categorize it. I want to know which galaxies are similar, which ones are different. So I can actually do cluster features, and I can look for cluster features and look for ones which are similar or which are different. So here it's broken it into 3 different clusters, 0, 1 and 2. 0 has 1001 galaxies, 1 has 2994 galaxies, and 2 has 5. So 2 is some outlier class, and these guys are the major ones. So these are this and these are this. So then you can worry about what's the difference between this and this. So if you plot a figure and you actually look for these these things, you will see cluster 1 is the one in blue, orange is cluster 1, sorry, cluster 0 is in blue, cluster 1 is in orange, and cluster green is the outlier, which just makes up 5 of the galaxies. Okay, so we may do k-means clustering. This is the k-means clustering in PC1, PC2 space. So when we've plotted it in PC1 and PC2 space, if you remember, we've earlier also spoken about clustering. We can do clustering. Here we are using k-means, and we get these different types. So now we can use this to discuss our result. We've reduced our dimensionality, and instead of 1000 dimensional spectral, we've reduced it to 5 or 20 or 3, right? The first component tracks the dominant continuum sequence, while you have this thing. You have PC2, PC3, line variations, and outliers are also valuable, and clusters are interpretable but not definitive. So here what you see is that principal component analysis is linear, spectra may have non-linear structure, component signs are arbitrary. So you will be having this thing with you, so you can complete it. It's almost over. So thank you. I'll end with this and take the questions on the chat. So, oh, I think all these chat ones are all the AI ones, AI generated ones. I thought there were so many questions. I was happy. But these are all, okay, AI generated. So Sampreet Das has a question. We are facing a bit of confusion regarding number of, these problems I will not solve. Number of projects and what to do, that is not sorted by me. That has to be solved by Lebo. Lekolane will do that. I don't know about that. Till then, you tell me if there are some other questions. Please tell me any other questions which you may have. Otherwise, we can stop. But let me know if you have any other questions. Not about capstone project. Yeah. I just gave you ideas of what you can do with your capstone project. So typically, if you take up such a task with AstroML datasets, you can take up a task of principal component analysis and work it out. You already have our notebooks, you just need to re-edit it, right? And figure out what to do. I don't see any questions. So maybe we can stop. Are there any questions? You can unmute yourself and ask. Okay, wow, there's a question. Can we do line fitting for molecular? Yeah, you can. You can do line fitting for molecular spectra also. It doesn't make a difference. You just need to have the spectrum, you need to know the wavelength, and you can do it. It needn't be atomic, it can be whatever you want. Santosh Kumar. You can do line fitting for molecular spectra, yes. Only the way you'd fit it will be slightly different, but it's about the same thing. Yeah. Anybody else? Any more questions? Okay. Lebo, we can wind it up.
Thanks, Priya. That was wonderful. So maybe let me start by addressing, I guess, the question in the chat. So for week 9, we haven't put any assignment yet for week 9. So because we haven't gotten the material for week 9 as yet, so they can relax on that regard.
Yeah.
And then we set the deadline for receiving the last capstone is the 28th of July. So it gives them roughly 2 to 3 weeks to work on the capstone project after we've concluded the program. So they can submit it anytime, because they were I think we said that they can start working on it anytime from week 5. So I think that's more than enough time for them to work on the project. So I'm not sure. I hope that deals with the questions, because the date is the 28th of July. So not of June. So because we still be within the program. So I hope that deals with the program. But to Professor Priya and Professor Najam, thank you so much for this wonderful
One second. There's
Yes.
somebody who's asked, I'd like to discuss about application and feasibility of AI/ML into the field of modern astrophysics. It's a very broad topic, so please individually ask and we can answer your question because the thing you're talking about is a bit too broad. AI/ML in the field of modern astrophysics. So you tell us what you're talking about. Yeah, Lebo, sorry, take over. Yeah.
Okay, perfect. So thank you so much for this wonderful lecture. So for the participants, remember you can still rewatch this on YouTube. It's available under the tab of live stream, so we should be fine. But thank you so much, Priya. We can we can wrap it up here. Thank you, and also Najam, thank you.
Bye-bye.
Thank you.
Bye-bye.